All right, so let's just get started, I guess. So Mike gave a really good introduction, so I'll just jump right in. But just a quick recap, I'll just give you a very introductory tutorial on deep reinforcement learning algorithms with DQN and TensorFlow. So it is really introductory. If you guys have been looking at any tutorials online, or if you've taken the previous offerings of machine learning by Pascal, you probably know what I'm talking about. OK, so just a recap. Here we have the very simple reinforcement learning loop. So it's a very simplified view, but when you're actually implementing deep reinforcement learning algorithms, a lot of times you just have to implement the stuff that you see in this loop. So really, you just have to implement the agent, you have to implement the environment, and you just have to implement the logic that connects the agent with the environment. Right, so the environment, the agent, and just the logic, which usually manifests itself in just this large while loop and to execute a number of epochs. I think Mike touched upon this one in his talk. So luckily for us in our course, like the environment's mostly taken care of by the OpenAI gym. Of course, then it is still a really good exercise if you still want to like continue to do more deeper research into machine learning and reinforcement learning to implement your own environment is a good exercise. But for our course, it's mostly we're just going to use OpenAI gym. I think depends on what Pascal does for his assignments. So I'm just going to talk just briefly on the agent. OK, so like I said during the tutorial, we're going to use DQN for the agent. And so just a very quick recap on where DQN comes from. So in the beginning, the goal is we wish to learn the state action value QS of t for all states and actions. So as you recall, the state action value just tells you, like, in a certain state, taking that reward, how good the agent thinks like that state action reward is. And so recall from Bellman's equation, you can unroll this, and we have this relationship. So Q of S of t, A of t is equal to the reward that you get for taking one step, and then the max all of that for the next state that you landed. So then having this equation, you kind of get like some kind of error signal. And so using this error signal, you can define a loss function, which I'll explain. So to get this loss function, you just take the difference of both sides. And when it converges, it should be 0. So when it doesn't converge, you're going to get some error. And that's going to be your training signal. And what we can do is take that error and use what's called the mean squared error loss. It's mean because what we're going to do is we're going to take the average over the number of samples that we see. That's going to be our batch size. And it's a squared error because you take the loss function here, and then you're going to square it. So it's pretty simple, mean squared error. So here, this is also known as your target. And this is your current estimate. And basically, what you want to do with this algorithm is you want to move the gradients so that your current estimate gets closer and closer to your target. OK. So usually, the Q values, the states and actions coming could be really high dimensional. So we have to resort to something called function approximator. And so basically, we just parameterize the Q values with some kind of function approximator with weights W. You can use any function approximator that you want, like a linear regression. Excuse me. But usually in this course, because we're doing deep reinforcement learning, and deep just means that the function approximator is going to be parameterized using an artificial neural net. So in here, weight W just denotes the weights of your A and N. Oh yeah, and one last thing I want to mention is usually for your target value here, this is usually held constant because when you're training, if you don't hold this constant, it will cause instability issues. So W bar just denotes the fact that when we're training, the weights of the target Q are being held constant. OK, so just pictorially, if we can zoom into the agent, this is just what it looks like. You just have like an agent that's parameterized by a neural network. So you just have a state, and then you're going to feed that state into some neural network that's parameterized. In this picture, it's theta, but then in my slides, I put as W to be consistent with Pascal's lectures. And then you're going to output some policy. Well, specifically for us, it's going to be Q values, but you can extract the policy using implicitly by finding the arg maximum of the Q values. OK, yeah, so let's just actually look at some code that does this. So basically, it's a very simplified view. What we're going to try and do is we're going to parameterize the Q value using an artificial neural network. And the specific artificial neural network structure that we're going to use, I'm going to have the input state dimensions. The number of hidden layers is going to be 256, 256. And then we're going to have kind of the number of actions that come out as the output layer. And then we're going to see how we're going to specify a loss function. So that's just going to be the first part. So before we actually look at the code, I want to emphasize that in TensorFlow, there's kind of like a natural division between two phases of execution of code. The first part is, in the first phase, all you do is you're going to build a computational graph. So at this point, there's no numerical computations, and all you're doing is you're just having code that specifies what connects where. And in the second phase, you run something called the TF session, and in this case, it's kind of the opposite. In this case, you're actually performing like the numerical computations. You're doing the matrix multiplications, and then the tensors flow through your computational graph, hence TensorFlow, and make computations. So some example of thing that gets done here is kind of like the initialize the weights. Your tensors are being passed in for like a forward pass, and then the tensors are being calculated with gradients to be backpropped. So I want to make this distinction because when we're looking at the code, you can see like which part where we're just kind of declaring the computational graph and which part we're actually making the kind of the computation, numerical computations. So in the beginning, we just import the TensorFlow libraries, and then here I have the agent. As you can see, this is contained within a class. So if you're starting out with Python, I would recommend using a class. It's really nice to encapsulate all the stuff that you have. And so in the beginning here, we just taken the parameters for the input and the action size and the scope. So this is basically the constructor. So whenever I call the class, this gets executed. And as you can probably guess, this is just the part where in the beginning I parameterize the neural network and I just specify the structure of the neural network that the agent's going to take. So at this point in time, there are no computations being taken place. So in TensorFlow, there's something called placeholders. So placeholder is just basically a variable that says like, oh, okay, this is going to be, as the name suggests, a placeholder that will receive some kind of numerical value when execution happens. So as you can probably guess, the states and actions are going to be the inputs, right? So this is kind of the input layer of your neural network. And then really, it's pretty simple. Like the syntax is pretty simple. Here, the next part, what I'm going to do is I'm going to construct the fully connected layers. So as you can probably read from this syntax here, I'm going to feed the states in. And this just means that the number of hidden unit is going to be 256. And then the activation function I'm going to use is the rectified linear unit, which is 0, max of the input. And so here, then the return is just the fully connected layer. And then I want another hidden layer, so then I just feed the first fully connected layer back into another fully connected function that does the FC for you. And again, same thing, it's just 256, same activation. And in the end, this is the output layer, and then this is when you actually define your Q values. You feed the second fully connected layer back in, and in this case, the activation is none because you want your Q values to be able to take any value that you want. So you don't want it to restrict it to be 0 max. That way, it won't be able to take any negative values, and that's not good. I just also want to mention that I'm using a library called Slim here. This is basically a high-level library that lets you call fully connected layers just using a high-level library call that just goes fully connected. If you didn't use this, you're going to have to define your like weight matrices. You're going to have to use tf.matmul, and you're going to have to call your custom activation functions manually. You could do that. It just gives you like a more of a kind of like lower-level access to how to manipulate the arrays. And then afterwards, I just define the loss function, which I showed you back in the slides, which is the summation, the mean squared error. So so here again, before we go there, we have a target Q network. So this is going to be the target that I'm going to take in. I'm going to define a placeholder for it. And then using this target and using this is going to be a current estimate, we're going to construct a loss function. And then afterwards, we're going to declare an optimizer. And here we're going to use the atom optimizer. And so you just call it, and this calls the initializer. And then you just call the minimize function, and you just put the loss function in. And all this does is just allocates a symbolic variable that when you call this later on, it's going to minimize what you're going to put into here. Any questions so far? Yeah.
What is null here?
What is, I'm sorry?
Null.
Oh, okay, right, none. So in the beginning, when you declare variables or when you declare placeholders, you have to specify the size of your variable. So that way, the language, when it will know ahead of time the array dimensions that you're going to pass in. So this is one little restriction of the language that it has to know what you're putting in. But specifically with the first dimension, you get to leave it as none because usually the first dimension is your batch size. And usually when you're training your neural network or you're training any machine learning, sometimes your batch size varies. So it can be like 64, 32, and it sometimes varies through runtime. And so by having none, it just says that this dimension varies. And as far as my understanding goes, you can only have one dimension in your shape that is none. Everything else must be like none, and then like say like 2, 3. You have to specify how big the array is going to be. So right here, the input shape is that I use it as an argument to pass in, and it's none, 4. So it just means that in the beginning, I'm going to have the batch size, which will vary, and then 4 is going to be the state. Is basically the state dimension. Usually the state dimension is theta, theta dot, x, x dot, where x is position. So x dot's velocity. Does that make sense? Okay, let me just quickly now talk about kind of the logic that glues the agent and environment together. Mike really just touched upon this, but we kind of prepared separately, so I'm going to reiterate some of what he just said. So really, the interaction loop between the agent and environment is a pseudocode that just looks like this. So for some number of epochs you want to execute, right? You're just going to execute this loop for some number of epochs that you specify. And then in the beginning, you're going to initialize the environment, and then you observe the initial state that you're in. And then you keep performing this loop until the epoch is not over. And so at this point in time, you're in state S. And what you do is, having observed state S, you're going to take some actions according to the agent. So usually it's kind of like the best action that the agent thinks thus far. And then what you're going to have to do, though, is you're going to have to augment it with exploration policy. So if you remember from Pascal's lecture, he just kind of quickly touched upon this, but I think when he gets back, he'll talk more about it. But you need to balance between exploration and exploitation. And so usually, when you take an action that's given by your agent, it's the exploitation phase, and you're going to have to add some kind of exploration policy. And usually, one very simple and popular is called epsilon greedy, which just means that for some value epsilon, you're going to take exploitation approach, and some 1 minus epsilon, you're going to do a random action. And so once you have that action, you're going to step through the environment, which you can call by the OpenAI gem. So just environment.step, and then you're going to receive some kind of next state and reward feedback. And so you can update the exploration policy because, as time goes on, you want to exploit more than you explore. Then you can cache the training tuple, so S, A, R, S prime. This, in reinforcement learning, this will be your training data. You update your agent, so this is going to be the optimizer that you just looked at. It's going to be gradient descent. And then you're just going to update the state that you're in. And it's really about it. So I'm just going to show you some of the code that does that. So it's a very small code base. You can create an agent with very few lines of code. I only have 3 files in here. And each file is just like 50 lines of code. So in the beginning, I just parsed the arguments. So this is pretty simple. So I declare an environment, and then I specify the action size and the input size. So here, I initialize the agents. And remember that during the beginning, I said that you're going to have a target network that will keep constant when you're updating the argmax of the target. And so we have to allocate a target network for that. So this is here. And then I have to have an update parameter that will copy the weights over from the target net to QNet. I'll explain it a little bit more when we go down. So here, as you can probably guess with the TF session here, this is, it prepares a session. So it just tells the TensorFlow that I'm getting ready to pass in arrays into my computational network and actually perform numerical computations. So this is, as you can probably guess, so this is where we're going to start to calculate gradients, do forward passes, and et cetera. So per the pseudocode, we're going to execute for some number of epochs, right? In the beginning, we're going to reset the environment. So this onth.reset Mike kind of talked about. You just reset the environment, and then you receive your initial observation. And then while true, and so I have it's while true right here, but then I have some logic to check if the epoch is over. So it's really while epoch is not done. What we're going to do is So this part of the code does the epsilon greedy, is part of the epsilon greedy exploration exploitation strategy. So if it's less than some epsilon, I'm going to choose a random action. So we're in the exploration step right here. And then else, we're going to do exploitation. And what I'm going to do is I'm going to tell my agent to act. And then I feed in the state and the session. And the session, so it's just some variable that in TensorFlow that allows you to propagate the values forward in the Q network. So after in this part, I have an action. Then using this action, I'm going to step in the environment, and then I'm going to receive some kind of feedback from the environment, right? So it's going to be the next state, the reward that you get, and then whether this variable here just tells you whether it's done, whether the episode is over or not, the epic is over or not. So here, this is just me just catching some statistics. I just want to see the total rewards. Then here you can add these training tuples to your memory. I think Pascal will talk a little bit about this later. This is called the replay memory. And it's just a fancy word of saying that this is just a cache that will collect all of the experience that you've seen. And it's usually a first in, first out cache. And then you can random sample from it to train your agent. Actually, the replay buffer is also like something that's active in the research. So right here, we're using a random sampling policy in the sense that everything is weighted the same. Each tuple inside the memory has equal probability of being taken from, being sampled from. But there's other like more sophisticated policy that does like prioritized sweeping and things like that can better sample the experience. Here, so what I'm doing is reducing the epsilon. So this is me changing the update policy. So I'm going to anneal the epsilon rate, meaning that as time progresses, I'm going to exploit more than explore. And then so here, this is where I actually perform the training step. I take a batch, I sample a batch from the replay buffer, and then I'm going to feed that into the training step inside the agent. So here, I'll step to the functions and show you what they're doing. So really, it's just act and train. And then set the next state. And then here, here's just an operation that will periodically update the target network with the previous network. So that way, it keeps updated from time to time. You're going to have to do that. And then right here, I just, if done, then I just break out, and then I can restart the loop. So really, the parts I haven't really talked about then is just the agent.act and agent.train. So if we go back here, it's just these two functions, and that's it. So in the act, what you're doing is you have the state, right? And then so the syntax to actually run your code through the computational graph to get some value, to get some output value of a neural network is sesh.run. And here is the value that you want to extract from. And so this is the Q values that I want. And then the feed dictionary just means the value that I will have to feed into my neural network in order to get the output. So here I have to feed in the state, and that's it. So the return is just the Q value for each action output. And then the action, the optimal action, the current estimated optimal action is just basically the argument maximum of the Q values. So that just returns you just like a one-hot vector, and then you can just step through. And then the train function, so basically you have a batch that you input in, learning rate, and then you also have the target network. And so the code is pretty self-explanatory. So here you just extract the states, the actions, the reward, the next states, and the dones from your batch. And then what you're going to do is this right here. It does the TensorFlow computation to get the next Q values. Remember, recall that in the loss function you have R of t plus gamma times the arg maximum of the next target value. So you're going to have to feed in the next values into the target state here, and then after that, this will get you the kind of Q values for the next state. And basically, you just have to write this equation in code, the equation that is so it's basically, that line of code implements this loss function right here. Right. And then in the end, the next Q is prepared, and all you have to do is just feed this into, sorry, give me 1 second. And then all you have to do is just feed this into kind of your session. And so it says that for the given state, given action, and the given target, you're going to update the model. And then if you recall, the update the model, then it would just perform this in the back end, which would just minimize this loss function that you've specified. And so that really all is to it. And then TensorFlow does everything. Yeah. So let me just give you a quick demo of this code when it's actually running. So here I'm going to run it on a simple cart environment. So I think Mike kind of explained it. And basically the goal is just to bounce a cart. So when I run the main loop, so what's really nice about the gym environment is that there's a render function that you can see it watch it as it's training. So now right here I'm just also printing off the statistics. So in the beginning it's kind of doing bad. It's just getting like these. The episode's over once it's past a certain angle, like it tips over. So I'm just printing the statistics. We're at epic 45, and so now as time goes on, it begins to improve. You can see, right? Yeah, and so that's all I have. Thanks.